Alright, the last video introduced some rotational kinematic quantities. This video will continue with that discussion and introduce dynamical rotational quantities. So in particular, we're going to get the rotational analogs of mass, momentum, force, and we'll talk about, and then this rotational version of mass, that's actually the first thing we're going to do. We'll conclude the video with calculating this thing. This will involve a little bit of calculus too. So this video, we're just introducing this, giving you a flavor of what, for example, torque and angular momentum are. We'll be studying it in a lot more detail in the next couple chapters. So chapters 10 and 11 just further expand on some of this stuff. So this is more so an introduction to these quantities. Okay, so after we talk about the rotational version of mass and energy, we'll be able to answer this question. Okay, so to see where this rotational version of mass comes from, I want to consider a rigid body with that pivot point. So this piece of mass is comprised of, a bunch of little masses, and we're just going to focus on one of them, this mass right here, m sub I. Okay, so later on, we're going to sum over all the masses and see what spits out. So this mass is some distance away from the pivot point. That should have been a straight line. Some distance away from the pivot point, and that distance depends on which mass we're looking at. So that's why I'm going to add an I to the subscript. So r sub I depends on which mass we're looking at. And if this is a rigid body, then this thing is just moving perpendicular with some speed that equals the angular speed of the body times the distance. Okay. The kinetic energy of that object, of that little mass, m sub I, is 1/2 mv squared. Okay, where there's just an I subscript labeling which mass and it has its own velocity. Okay, so we could rewrite this way. 1/2 m sub I r sub I squared times omega squared. Okay, that's for each piece. Now, if we want the total kinetic energy, this is going to be the total rotational kinetic energy. So we're going to expand on this next chapter a bit more on rotational versus translational kinetic energy. So if you have a rigid body about a pivot, you can separate it out into these two pieces, translational and rotational. All of the energy here, so if the pivot isn't moving in this reference frame, all of the kinetic energy will be rotational kinetic energy. So we just need to sum up all of these pieces. So the total amount is going to be a sum over all the masses, I. And we're summing each individual kinetic energy. Okay? And your book does exactly this. So I'm matching your book for now. I'm going to diverge a little bit from your book, talking about torque and angular momentum, and then come back to what your book does for section 6. Okay, so summing over all masses, we can actually write it this way. So the 1/2 is common to every piece. And if we plug in for V, so remember, V was R times omega. So V squared would be R sub I squared times omega squared. And we could factor out a 1/2. And we could factor out a omega squared. Okay. So the reason we're doing this, the reason we're looking at this, is that this really motivates what the rotational version of mass is. So this is the rotational analog of mass. So the total kinetic rotational energy, so the rotational kinetic energy, is 1/2 some rotational version of mass times the rotational version of speed squared. So just like we had 1/2 mv squared for the linear quantities, 1/2 mass times speed squared, we have 1/2 times rotational mass times rotational velocity squared. So this thing in square brackets is the rotational analog of mass and it has a certain name. It's called the moment of inertia. The moment of inertia. And it's given a symbol I. So if you have a rigid body, you can compute I. It's the sum of the masses times how far each of the masses are away from the pivot point. So this is if you can separate your body into discrete pieces. For a continuous body, you would have to integrate all of the little pieces, dm. So you might freak out and say, well, why did you put dm in front of the r squared? So maybe this is the first time you've seen this, but it's actually pretty common in physics to write this piece before this piece. So even though like r squared is not a constant, and you would in a math class you'd be yelled at if you wrote that, because you really need to put everything within the integral sign and the d whatever infinitesimals. In physics, we do this. And one reason is that, later on, if you keep going in physics, sometimes you'll write an infinite number of integral signs. So you'll do something like this, and you'll have to do dx1, dx2, an infinite number of times. So you specify that first, and then you say what you're going to integrate over. So just kind of a notational thing. Okay, So towards the end of this video, we're going to figure out how to calculate some of these things. So actually, bam, put these, that was magic, right? So actually I have some of these values for moments of inertia of some common objects. So we're actually going to prove one of these later in the video. We're going to prove this one, this F, solid cylinder. So solid cylinder, solid disk, same thing. So we'll prove this one, and actually for the example problem that we have, we're going to need this and this result. So you'll see this. So I want you to so maybe to talk about moment of inertia, I want you to notice. So first, let's look at this. So this depends on where the mass is distributed. So moment of inertia is more than just mass. It's how far the mass is away from your central axis. So like if all of the mass, so pretend you had a rod that it was very, very thin rod, and then all of the mass was right here and right here. So most of the mass was at those two ends. If it was spinning at some angular velocity, it would have more kinetic energy than if you had something like this, if most of the mass was at the center and then a thin bar. So if that was rotating at the same speed, this wouldn't have as much energy as the other one. Okay. Another way of thinking about mass is how much it makes something hard to accelerate. So like something that has, so if you picture like a really big massive box versus a light box, and you give it the same force for both of these two boxes, the light one is going to accelerate more. Okay, so in the same way, if you had two rods, these are supposed to be the same, and you were given both of these, and you twisted, and like you were just kind of you grabbed the center and you just kind of flick it back and forth. If you had a rod where most of the mass is in the center versus most of the mass at the end, the one where most of the mass in the center is easier to flick around, to move around. Even if they have the same total mass, if more of the mass is at that central pivot point, if you're rotating around the center, the second one would be easier to rotate rather than the top one. Okay, so the rotational version of mass depends on mass, but it also depends on where the mass is distributed. That's the point. Okay. Rotational inertia, also called moment of inertia. So the moment of inertia is a sum over all the pieces of mr squared. And here it looks like there's only 3 pieces. That's why the I went from 1 to 3. But in principle, you can have any number. Okay, so more on that later when we compute some. Okay, so now I want to start to fill out this table of linear quantities versus rotational. So we're adding to this story rotational. So before we had x, v, acceleration, and time was still time. And the rotational versions of these are angle, angular velocity, angular acceleration. Time is still time. So that was last time. And we're adding to this. So now we're saying that what was mass is now going to be moment of inertia, I. And we have a definition here. So I is actually the integral of, and I guess I'll write it in a way your math teacher wouldn't hate. Integral of mr squared over all the masses, over all the mass pieces. So that's the definition of I. So we're gonna take some linear equations, and every time you see m, you're gonna replace it with I, right? To get the rotational analog of that equation. The next two things that we're gonna talk about in your book, well, I'll talk about what your book does in a little bit, but I'm going to talk about it in a way that most other textbooks would talk about it. We want the linear versions, or we want the rotational versions of force and momentum. Okay, so actually I'm going to start, so especially on this and this, remember we used to have vector signs, and there's vector signs associated with this and the right-hand rule. So in your SI sessions, you're going to talk more about the directions of these things. But it's really going to come into play here with forces and momenta. The rotational version of force is torque. And we're writing down the definitions here. The definition of torque, it's like a force, but it's a force that tends to twist or rotate an object. Okay, so let me write down the definitions, and I'll give you a little bit more flavor of how you would go about computing this. But the torque, the torque is R cross F. And so this is the rotational version of force is torque. This one was moment of inertia. Remember, these are new ones that we're introducing this video. So moment of inertia I, torque tau. And we have the rotational version of momentum is angular momentum. And the letter for that is L. And this is R cross P. So with these definitions, so I'm going to talk about this and this in just a second, but but with this sort of dictionary, I just want to point out that you can guess what a lot of other equations are saying. So before you had Newton's second law. So sum of the forces is mass times acceleration. Okay. So this is telling you what's pushing or pulling on an object. This is going to tell you how it's going to move. There's a rotational version of Newton's second law, and that is that the sum of the torques on an object equals, and you can guess exactly what these are by plugging in the rotational versions of these two things. So the rotational version of mass is moment of inertia, and the rotational version of acceleration is angular acceleration. Sum of the torques on a rigid body is the moment of inertia times the angular acceleration. So if you want to change how fast something is spinning, there has to be a net torque on the rigid body in order to change omega, right? That's what alpha is. That's what angular acceleration is. It's a changing angular velocity. Just like you can write momentum in terms of mass and velocity, you can write angular momentum as I times omega. Now this only works if you have a rigid body. So actually the definition that I wrote down here is more general than this, because we're going to want to consider angular momentum of a point particle in addition to a rigid body. Okay, and we've already got a flavor of this when we talked about like the motion of planets around the sun in Kepler's second law. We talked about angular momentum of a point particle rather than a rigid body. Okay, so actually using this definition, you can prove that for a rigid body, it looks like this. Right? So for a rigid body, the momenta points in a certain direction and it's related to omega in a certain way. And when you sum over all the masses, it winds up being moment of inertia, just times this constant for the whole rigid body. Okay. What's another one? Another one is to combine these two equations that I just wrote. Another way, remember that we talked about Newton's second law, was sum of the forces was dp dt, the change in momentum. And you can probably guess what the rotational version of this is. The sum of the torques on an object is the change in angular momentum with respect to time. Okay, so a lot of next chapter is exploring these consequences and how to deal with these quantities and problems. Okay. But what I want to do right now is, well, actually, maybe I could do a couple more. Actually, let me add a few more things. Okay, so kinetic energy, translational kinetic energy. This one we've already written down. 1/2 mv squared, the rotational kinetic energy. So energy is still energy, but we're labeling the types of energy here. Rotational kinetic energy is 1/2 I omega squared. We also have work is force dot displacement. So this is like translational work. You can also talk about work done in the rotational context, and this is a torque over a change in angle. Okay, if something is providing a torque through some angular displacement, that object that's providing the torque is doing work on the rotational body, either positive or negative work. So adding energy to the system or taking it away. Okay. Now, I guess you could put subscripts here, translational and rotational. Sometimes this gets a little confusing because the energy, maybe the translational energy is going back and forth between translational and rotational energy. So actually static friction does this. Static friction will turn one of these into another. So like static friction, this would be positive, this would be negative, and they'd be equal and opposite. So overall, no work is done by static friction, but it'll, change where the energy is. Okay, so this is just kind of a preview of things to come. Okay, so actually we are in a position now where we could solve this problem. So maybe before I go into a little bit more about torque and angular momentum, let's solve this because we can. The moment of inertia, so we have a bike wheel with 6 spokes, all of mass m over 12, and then the rim is m over 2. So half the mass of the wheel is in the 6 spokes, and half of it is in the rim. We want to know the moment of inertia of the wheel. So that the moment of inertia is the sum of this moment of inertia of all 7 pieces about this pivot, right in the middle. So for a rod, each of these spokes is a rod where the pivot is at the end of the rod. That'll be this equation right here. So the moment of inertia for each spoke is 1/3 times the mass of that spoke, which was 1/12 times the total mass of the wheel. And then L is the radius of the wheel. It's the length of the rod, which here is the length of the spoke, which is R, the radius. So there's going to be 6 of those, and then we also need the moment of inertia of the rim. Now the rim, or a hoop, has a pretty simple moment of inertia because all of the mass is at the same radius, R. So if you're summing over all the pieces of mass here times R squared, well, the R squared you can take out of the integral sign, right? If all of them are at R equals capital R, you could take this out of the integral sign and it's the total mass times R squared. So, if all of your mass is at the same distance from the pivot point, that's easy. It's these complicated shapes. It's because some of the mass is close here and not all of it at like L over 2. That's why this number is less than, I suppose it would be 1/4 ml squared because all the mass would be at L over 2, and when you square it, it would be 1/4. So if all the mass were at this end and we were rotating about the center, then the moment of inertia would be 1/4 ml squared. Okay, but here some of the mass is closer, so it's 1/12 ml squared. Okay, so to actually compute this, you have to split this up into a bunch of infinitely small pieces and then integrate over the whole rod. So we'll get a flavor of that at the end of the video. Okay, so for our original problem, we're doing part A. We're calculating the moment of inertia for the whole bike wheel. This is the moment of inertia. This is 6 times the moment of inertia of one spoke plus the moment of inertia of the rim. So this is 6 times, and then for each spoke, remember that's the moment of inertia of a rod about the end, and that was 1/3 times mass. And we're told the mass of each spoke is 1/12 m. 1/3 mass times L squared. That's the radius of the spoke here. And then for the rim, remember that was easy. That was just M, which is half the mass of the whole wheel, mr squared. Okay, so it looks like, so 6/3 is 2, 2/12 is 1/6. So this is 1/6 plus 1/2 mr squared. Looks like this is 2/3 mr squared. Okay, so that's the moment of inertia of our bike wheel. And if it has angular velocity omega naught, or angular speed omega naught, then the rotational kinetic energy is 1/2 I omega naught squared. And so we just plug in for our value of I. Looks like I is 2/3 mr squared. Looks like it's 1/3 r squared omega naught squared. This is the kinetic energy, the rotational kinetic energy. And I believe that was the question. Yeah, given omega naught was the rotational kinetic energy of the wheel. So this describes how much work is required to get that wheel spinning up to final angular speed omega naught. Okay, so like if this came from a constant torque, you could use the rotational version of the work energy theorem. I'm thinking right here. So set the final kinetic energy equal to tau times the angular displacement. And if you knew one of these two things, you could solve for the other one. If you knew how quickly, how many, maybe this thing got up to this final speed in one revolution, you could figure out what torque it takes to do that. Or maybe you knew what the torque was and you could figure out the angular displacement. Okay, so I want to give a quick introduction to what torque is all about. So torque is R cross F. So your book explains this the way I think about this also. So suppose you have a door, like this is like a bird's eye view of a door, and you have some force that you could use to get the door to swing open. Should you apply the force here, here, here? Where should you apply it? Well, the farther you are away from the pivot, the more efficient you are at rotating the door, the more torque you provide. Okay, so this explains, so R is the distance from the pivot to the point where the force is applied. So we want that to be as big as possible. We also want the force to be as big as possible. So I'm imagining it's the same force at different positions. So we probably want it over here. And from your experience day-to-day life, you're probably not going to pull this way, right? You're not going to go this way. You're going to do it perpendicular to the moment arm. So R is from the pivot to the point where the force is being applied. And then F is, so the force is being applied at some point, and then the force has some vector. This cross product is a vector in 3D. So if you use your right hand, and your SI leaders are going to talk more about the right hand rule, R cross F is pointing out of the page. So here, this gives a torque, tau, which is R times F times sine of the angle between R and F. And I think your book uses gamma for this. So see the gamma right there? That's the angle between R and F vectors. So gamma, you can call it whatever you want. You can call it alpha, beta. Probably not theta, because theta we would use to talk about like where the angle that the door swings through. So you probably reserve theta for something like this. So probably anything but theta would work okay. So you'll see this written a few different ways. You could call this R times F perpendicular. So in other words, if F was like this, the only part that matters is the part that's perpendicular to the R vector, right? This parallel component wouldn't matter at all. Or you might see it as R perpendicular times F. So another way of looking at it, like if you had that force, is to draw a line for that force, and then it's this minimum distance that line of force makes with the pivot. So this is actually called the moment arm. This R perpendicular is what's called the moment arm. So a few different ways to think about this. So either R perpendicular, or you could talk about F perpendicular. So different torques. So on the door, there could be a bunch of forces pulling it different ways. Some torques are out of the page. Those torques which tend to rotate the door counterclockwise are torques that are out of the page. Those that tend to rotate the door clockwise would be torques that are into the page, using the right-hand rule. So like I mentioned before, you sum up all the torques equals I alpha. So this rotational version of Newton's second law. If you know how to deal with each torque separately, and then this rotational version of Newton's second law says the overall effect once you take into account all of those torques. Overall, this door is going to speed up. If if it started from rest, it's going to start moving in whatever direction those torques are. Okay, so that's torque in a few minutes. Angular momentum in a few minutes. So angular momentum is r cross p, not r cross f, r cross p. And so just like torque is the rotational analog of f and it's dealt with in Newton's second law, there are rotational versions of conservation of momentum, which are conservation of angular momentum, and we're going to explore that next chapter. So you can think of angular momentum as a tendency of, like, this thing has some motion associated with it. So whether you have a rigid body or not, so maybe you have a rigid body that's rotating, or maybe in addition to that you have just a point particle that's actually, it doesn't have to be attached to anything. Maybe it's just moving this way. So lowercase m, and then we have this whole moment of inertia for a rigid body. And this thing is rotating this way. Both of these two objects, I have I'm talking about the rigid body, and I'm talking about the point particle. Both of these objects have angular momentum about this pivot point. So you have to specify the pivot point when you're talking about angular momentum. Okay. When you talk about linear momentum, you don't have to specify an origin of a coordinate system or anything. But for angular momentum, you do. You have to specify what the pivot axis is, really. So the rigid body here, if omega is non-zero, the rigid body has angular momentum that's pointing out of the page. Okay, the way this is rotating, again from the right-hand rule. So this is if you took a bunch of little masses right here, and you did r cross p, so p would be pointing this way, r would be this. They're always perpendicular for a rigid body, r cross p. And you can write it as the moment of inertia of this rigid body would be L equals I omega. Okay, so L is pointing in the same direction as omega here. You're going to talk more about this on Friday. L doesn't always have to point in the same direction as omega. Okay, so so I shouldn't say that these are all going to nicely add up so that this points in the same direction as this. The point particle, okay, so L is pointing out of the page for the rigid body. The point particle has its own angular momentum. So you don't have to have a rigid body to have angular momentum. So for the point particle, you have this vector r pointing from the pivot axis to the point of the particle. And then the particle has some momentum p. So here it looks like r cross p is pointing into the page. The point particle, in this picture, the point particle has an angular momentum opposite in sign, or opposite in direction, as the angular momentum of this rigid body. And see how if the point particle were to collide with the object, it would tend to rotate it the opposite way? So like if this thing weren't rotating, if our rigid body weren't rotating and the point particle collided into this thing, it would tend to rotate the object in the clockwise direction, not the counterclockwise direction. Okay, so r cross p is how we take into account the angular momentum of each point particle, and we have to add them all up to get angular momentum. And the angular momentum, maybe it's conserved, maybe it's not. It depends on whether there are any external torques going on in the problem. But for problems involving collisions and explosions, we have conservation of angular momentum. So a lot more about that next chapter. Okay, and your book goes over this this table that I talked about a bit. Okay. And actually, this video is already getting a little long, so why don't I just keep it there to keep it to 30 minutes, and I'll talk about, in a whole other video, I'll talk about 9.6, calculating moment of inertia.